Have you ever stopped to think about how the apps on your phone or the websites you visit or the games you play actually work? It all starts as a human idea, right? Something written in a language that we can understand. But how does that thought actually become something a machine can execute? Well, let's follow that incredible journey of a single idea as it gets translated into pure action.
Yeah, it all comes down to this one big question, right? We have an idea in our head, but our computers, they live in a totally different world. A world of pure electricity, of just ones and zeros. So how do we possibly bridge that massive gap?
You see, at the absolute heart of the problem is a huge language barrier. We think in logic, in structure, in words. But computers? They only get the raw, super low-level language of machine code. These are two completely different worlds, and somehow they need to talk to each other.
And just look at this. It lays out the challenge perfectly. On the left, you've got a line of code that makes perfect sense to a programmer. But on the right, that's what the computer actually sees, a stream of raw binary. So how in the world do we get from point A to point B?
Well, what you need is a translator. And in the world of programming, that translator is the unsung hero of pretty much every piece of software you use. It's called a compiler, and its entire job is to be that crucial bridge between our human ideas and the machine's instructions.
So what is a compiler, really? In a nutshell, it's a special program. It takes the code that a programmer writes, we call that the source language, and it translates it into a target language, which is usually the machine code that a computer's processor can execute directly.
This gives you a great visual of the basic workflow. You feed your source program into the compiler. It works its magic, and it spits out a target program. But, and this is huge, look at that error messages part. A critical job of the compiler is to be your super strict proofreader, catching mistakes before the program even tries to run.
Now, you've probably heard of something called an interpreter. They're kind of like cousins, but they work very differently. A compiler is like translating an entire book before you hand it off to someone to read. An interpreter, on the other hand, is more like a live translator, whispering each sentence in your ear one by one. For today, we're focusing on the compiler, which does all that translation work up front.
All right, so what's actually going on under the hood of that compiler? It's not just some magic black box that instantly translates everything. No way. It's a highly detailed, multi-step process, a sequence of phases where each one has a very specific job to do. Let's crack it open and take a look.
Think of this diagram as the roadmap for our code's big adventure. Each one of these boxes is like a station on an assembly line. The code comes in, gets transformed a little bit, and then gets passed down to the next station.
Okay, so the first big chunk of this whole process is what we call the front end, or the analysis phase. Its entire job is just to understand the code that was written. And we can break that down into three main steps: lexical, syntax, and semantic analysis.
First up is lexical analysis. You know how when you read a sentence, your brain automatically breaks it up into individual words, numbers, and punctuation? That's exactly what this phase does for code. It scans the text and groups characters into these meaningful little chunks called tokens.
Okay, so now that we have our words, or tokens, we move on to syntax analysis. This phase is all about grammar. It takes those tokens and checks if they're arranged according to the rules of the programming language. Is the sentence structure correct? This part is also known as parsing.
And finally, we have semantic analysis. Look, just because a sentence is grammatically correct doesn't mean it isn't complete nonsense, right? This phase is the nonsense checker. It makes sure the code is logically sound. For example, it'll catch you if you try to use a variable you completely forgot to create. It's checking for meaning, not just structure.
Okay, now this is where things get really cool. Once the compiler totally understands what the code is trying to do, it gets to show off a little. Before it generates the final machine code, it actually looks for ways to optimize the program, to make it faster and way more efficient.
And I mean, it can pull off some seriously clever tricks here. For instance, it might unroll a loop to save some time, or get rid of calculations that are being done over and over for no reason. The goal is always the same: create the fastest, leanest version of the program possible, without changing what it actually does.
And you might be wondering, why does this matter? Well, it matters a lot to you and me. This whole optimization step is the reason your favorite apps launch quickly, why games run smoothly, and why your laptop's battery doesn't die in an hour. It has a direct impact on our experience.
So, let's recap. Our compiler has now analyzed the code, it understands it, and it has even made it better. But its job isn't done in a bubble.
It's actually just one critical step in a much bigger pipeline that creates the final program, the thing you can actually double-click and run.
And this right here, this is that bigger picture. The compiler has done its main job, producing something called assembly code, but now it has to hand off its work to the rest of the team. The assembler, the linker, and the loader all have to step in to get it across the finish line.
So let's quickly walk through this final stretch. First, the assembler does that last little bit of translation, turning the compiler's output into pure machine code. Then the linker comes in. Think of it like a project manager, finding all the other bits of code your program needs from different libraries and stitching it all together. And finally, when you go to run the program, the loader takes that final file, puts it into the computer's memory, and basically yells at the CPU, "Hey, time to get to work."
I mean, when you step back and look at it, the compiler does an absolutely incredible amount of heavy lifting. It's this complex, vital piece of software that, while mostly invisible to us, is a fundamental pillar of our entire digital world. It truly is an unsung hero.
So let's just recap why they matter so much. For one, they let us write programs in languages that feel natural to us humans. They then optimize that code for incredible speed. They can improve security by hiding the original source code. And, maybe most importantly for programmers, they act as our first line of defense, catching our silly mistakes early on.
You know, this quote just nails it. Compilers constitute the bridge between software and hardware. They really are that essential link. Without that bridge, all of our brilliant software ideas would just be stuck on one side, with no way to reach the hardware that could make them real. And that leaves us with a really interesting question to think about. We've traced this amazing journey from a single line of code all the way to a running program. But as our ambitions get bigger and our software gets crazier, we're talking AI, quantum computing, you name it, you have to wonder, how are these essential translators, our compilers, going to have to evolve to keep up?